All right, here's my second video over what I call putting it all together. That's where we're graphing polynomial functions. We're going to combine everything we've learned in previous videos to do this. So I'm going to start, if this is our fourth degree polynomial function, I'm going to start by looking at our dominating term here. And what that dominating term tells us is it tells us about the end behavior. Okay? And the first thing we look at on that dominating term is we look at the exponent. Since it's an even exponent, we know our end behavior is going to be matching. So our function could look like that with a bunch of stuff happening in the middle, or it could look like that with a bunch of stuff happening in the middle. When I say end behavior is matching, it means if it's going up on the left, it's going up on the right, or if it's going down on the left, it's going down on the right. And then I got to look at that leading coefficient. Our leading coefficient is a positive 2, so that means it's going to be this situation right here. Our function is going to increase as it goes to the left, and it's going to increase as it goes to the right. So I'm going to erase that other one. So we've kind of got our end behavior. Now let's find our zeros. And so what we do here to find our zeros is, this is a fourth degree polynomial, so we can't really factor it. Can't use like quadratic formula or anything like that. So what we're going to do is we're going to use something called the rational root theorem. And I'm going to take the factors of this number over the factors of this number to figure out what might be roots. So if I look at the factors of 9 over the factors of 2, the only factors of 9 are 1, 3, and 9. The only factors of 2 are 1 and 2. So what I'm going to do is I'm going to take each of these factors in the numerator and put them over each in the denominator. So I'm going to have basically 1 over 1, 1 over 2, 3 over 1, 3 over 2, 9 over 1, and 9 over 2. And I'm just going to write those out here to the right. So here's what we got. We got 1, 1 half, 3, 3 halves, 9, and 9 halves. So if I consider the positive or negative, that'd be 2, 4, 6, 8, 10, 12 possible roots. These are the only possible places that this function could cross the x-axis. Okay, it's going to cross at most 4 places. And so this gives us the starting place for our guess and check. So what I'm going to do is I'm just going to pick one of these values and I'm going to divide it out using synthetic division to see if it is a root. If the remainder is 0, that means it is a root. I'm going to start with positive 1, because why not? So if I start out with positive 1, I'm going to use synthetic division, so I'm going to use all the little coefficients. There should be like a 1 in front of the x cubed. So we have 2, 1, negative 19, negative 9, and positive 9. I'm just going to fly through the synthetic division real quick. So I'm going to add those, was that negative 27, and then negative 27 would be 18. So basically our remainder is not 0. That means positive 1 is not a root of this function. Our graph is not going to cross the x-axis at positive 1. So I'm going to kind of come up here to where I listed all my options. I'm just going to kind of erase the positive 1. And we're just going to go down the line and we're going to keep trying. So I'm going to erase this stuff and get ready to play this game again, but now let's try negative 1. So 2 times negative 1 is negative 2, add straight down. Multiply those and get a 1, add straight down. Multiply those and get a positive 18, add straight down. Multiply those and get a positive 9, add straight down. And voila, we got a remainder of 0. That means negative 1 is a root of our function. So I'll go ahead and plot that on the graph. We like negative 1. I'm going to maybe, however you want to note that, put a little check mark up there above negative 1. But then we're going to keep going with our reduced polynomial. Okay, so I have the polynomial, let's see, it's going to be 2x squared, or excuse me, 2x to the third minus 1x squared minus 18x plus 9. And actually I want to be color-coded. And so what I do is then I just keep going with this kind of structured guess and check, and I try more numbers. Note that with the 9 and the 2 that we have here are the same as the 9 and the 2 we started with, so I have all these same values to keep guessing. If that were to change somehow, then we'd have different values to guess. But then I'm looking here, and just to save you the time of this video of me just doing a blind guess and check, I'm going to jump to the next answer that works. How about let's go with 3. 3 is one that should work, so if I do this right, I should have a remainder of 0. And it does. So whenever I do positive 3, 1, 2, 3, I get a remainder of 0. So that's good. And now what we do is we've reduced our polynomial down to a quadratic. And I always like this part because once we've reduced it down to a quadratic, that means we don't have to do this guess and check stuff anymore. That would be 2x squared plus 5x minus 3. And then all we have to do at this point is factor this polynomial. Now, for the sake of time in this video, I'm not going to actually go through the process of factoring this, but what this would end up factoring pretty easily. We'd have 2x minus 1 and 1x plus 3. And so then these two factors will give us our last two roots. I would set them each equal to 0 and solve. This one gives us negative 3, because your root is going to be whatever makes that factor 0, and negative 3 plus 3 is 0. For this one, it would be a negative 1/2, positive 1/2. So now we have our four roots. We have 1/2, negative 3, 3, and negative 1. Those are our four roots. I'll go ahead and plot them over here in the graph. We've got our 3 already plotted. We've got our negative 1 already plotted. We have a positive 1/2, and then we have a negative 1, negative 2. Then we have a negative 3 over here. So there's our zeros, and so I am running out of space in this problem, but if I were to write the factored form of this function, we have the 0 of negative 1, so that would be a factor of x plus 1. We have a 0 of 3, so that would be the factor of x minus 3. We have a factor of 2x plus 1, and then we have a factor of x plus 3. So there's all our factors, but note they're all to the first power, and that's why I wrote it in this factored form. Notice we don't have any like 2 exponents or 3 exponents. And so that means that at each of these zeros, our function is just going to pass through at that point. There's no bounces and there's no wobbles. So if I'm coming up here, we've already established our end behavior. We know our function is going to go up this way, and it's going to go up this way. But what happens in between is it's just going to pass through at each of these zeros. It's going to pass through at negative 3. It's going to pass through at negative 1. It's going to pass through at 1/2. And then it's going to pass through at 3. And if I wanted to add a little bit of extra, our y-intercept is going to be a 9, so we could always plot that as a 9. But this is basically what our function is going to look like. So just a recap of the process. We looked at our dominating term to figure out end behavior. Then we used what's called the rational root theorem to do an educated guess and check on what our possible roots are. After I divided out a couple of those roots, our reduced polynomial was a quadratic, allowing us to factor and find the other two roots. Then I can plot each of those roots, and based on the multiplicity of those roots, in other words, the exponent that's on each of these factors, that tells us what happens at those roots. Since these are all first degree, we're just going to pass through each of those roots, and boom, you got a polynomial.